Hi there, everybody. Today we're going to start Chapter 10, and we're going to talk about parametric equations. This isn't really a calculus topic, this video, but it is a pretty good treatment of stuff that you've seen before in an algebra class or possibly in a pre-calc class. So let's get started. So the way we think of parametric equations is that we have a particle that's moving in the xy plane, just tracing out a path, and then we have arrows marking the direction of its motion. This is not a function the way we normally think of functions because it fails the vertical line test. But each coordinate is a function of time. So the idea is we could write a function just for this and just for that, and we're pairing the two functions in a coordinate sense. So whenever we have a third variable and x and y are both functions of that variable, the variable is called a parameter. We use t most of the time, but you can use any letter. And these two equations taken together are called parametric equations. So each one separately is really just a coordinate equation, but together they're called parametric equations. And every time you plug in a value of t, it gives you a point in the plane. And as t moves around, the point moves around, and the curve it traces out is called a parametric curve. So this is a little different than the curves we've seen so far in calculus, where the order doesn't really matter. When we do parametric curves, the order definitely matters, and we have to mark it with the arrow. And the parameter doesn't need to represent time. That's just the easiest way to think of it when we introduce the topic. We could use any letter, and t could represent, really, just any third variable. Okay, so we're going to graph one of these by hand, and then I'm going to put an arrow on the graph showing which way the curve is traced out as t increases. And you can see here that x is a function of t, y is a function of t. But when we draw the function overall, when we draw the parametric curve, it won't be a function of x or y, because it'll fail the horizontal line test, vertical line test. All right, so the way we do this is you just make a table with t, x, and y, and you just plug the numbers in, right? So if I plug -1 in here, I get 1 minus -1 squared, which is 0. 3 times -1 is -3, minus -1 squared is -4, and just plot that point on a graph. Plug in 0, you get 1 and 0 when you plug in 0. And just plug in the rest of the numbers and go one at a time plotting the points as it goes around. You can see the order that it started down here in the corner and kind of comes up this direction. So when you put the curve in there to show and you connect it smoothly, and then just drop some arrows to show the direction of motion. So if you're graphing these by hand, this is really the way to do it. You're not really required to graph anything by hand. We're going to be using the calculators to do everything else in this video. And there is the next video that I'm going to make is really just showing you how to do some of the homework problems, because there's some really advanced graphing options, and I'm going to make a separate video for that. Okay, another way that you can graph these functions is to just graph x and y separately as functions of t, and then just trace out the way the curve goes. So for example, let's say t equals 0, so we know that's one of the points that we have to graph, right? And just look on the graph where that would be. So when t equals 0, x is 1. So this is t equals 0 right here. Well, that means as we trace out this curve, the farthest to the right this parametric curve goes is the same as the farthest to the right that this curve goes, because this is our x graph. So you can see it starts off to the left, goes right, and then goes back to the left. And that's exactly what happens here, right? Goes to the right, turns around, goes left. Same thing with this graph. This is mapping out the y coordinates. So, when you plug in t equals 0, you get y equals 0, so that's here. And you can see that it goes up and then back down again. So from here, so t equals 0 is 1, 0, 1, 0. And you can see that the x coordinates show what happens in the x direction. The y coordinates show what happens in the y direction. So you can see here it goes up and back down. And then when we start here, it goes up and back down. So you can use these graphs to build these things. Again, that's covered more in the next video, but you have a couple of homework problems where you have to just look at the general, is it moving x or y? Is it moving up or down? Is it moving left and right? And you just have to sort of like piece it together as you map t across. All right, so one thing we can do in order to help graph these things is called eliminating the parameter. And it helps us draw the graph. So I'm going to show you how to do the graphing on the calculator as well. And then we're going to use that to sort of choose the correct graph from a list. And what eliminating a parameter does is it just gets rid of the t. So the first problem we saw, example 1, you're not able to eliminate the parameter because it's not a function of x or y, right? If you go back and look at this function fails the vertical line test and the horizontal line test. So it's a function of t, but it's not a function of x or y. The rest of the problems we're going to see, at least the next two that we're going to see, we can eliminate a parameter. And one other piece of vocab. If you have just a general curve, the starting point is called the initial point, and the ending point is called the terminal point. Most of the time in these problems, you will have a beginning and an end point, but it's not required. On a closed interval, as shown here, it will be required. But in general, the domain of t is allowed to be negative infinity to infinity. It just usually isn't. All right, so we're going to eliminate the parameter to find the Cartesian equation of the curve here. And then we're going to sketch the curve and indicate with an arrow the direction in which the curve is traced as the parameter increases. So first thing I'm going to do is I'm going to see, I always graph these first. I recommend you graph these first. Because if this is a common type of graph, hold on, let me move my microphone here. If this is a common type of graph, it gives you some idea how you should approach the problem. So here's how you graph it on your calculator. So go ahead and just pause this and type all this stuff in your calculator right now. Right, go to Parametric, type in the equations, type in the t min and max here. The t step is up to you. Anything between like 0.05 and 0.5 works fine usually. And then I used zoom fit. If you already know the size of the graph, you can just type it in. If you don't know the size of the graph, go to zoom fit. Right, we saw that earlier in the class, how to use zoom fit. And then I usually just back off the window a little bit. So when I did this graph, I actually got a really nice graph. It looked like this. So I didn't need to change anything. And you get the top half of a circle with radius 1 centered at the origin. So the general equation of a circle is x minus h squared plus y minus k squared equals r squared. We're going to use this a couple of times in this video, so make sure you know this formula. H and k are the coordinates of the center of the circle, and r squared is obviously the radius squared. So here, the radius is 1, so 1 squared is 1. And it's centered at the origin, so h and k are both 0, so you just get x squared plus y squared equals 1. So we're done, basically. We eliminated the parameter. It's a half of a circle. The last thing we have to do is put the arrow on here. And one thing you can do is you can notice that our starting point, so we went from 0 to pi. Our starting point, when we plug in x of 0, it's just cosine of 0, it's 1. And sine of 0 is 0. So we're starting over here at 1, 0, and you can see there's only one path to take. So you draw the arrow in the direction that the path takes. So that first one's not too bad. All right, let's do another one. So I'm going to do the same sort of thing with this problem. I'm going to draw the graph first and see if looking at the graph gives me any idea about how to eliminate the parameter. So I messed around for a couple minutes and I got a pretty nice looking graph. And I noticed to me it looked like an exponential function. So when I eliminate the parameter, I would expect this to be an exponential function. So I looked at the x-coordinate equation. X equals natural log of t. And I thought to myself, if I solve this for t, I'm going to get e to the x. So already it's looking like an exponential function. But I still have to plug this into the y-coordinate to eliminate the parameter. So when I plug in e to the x into square root of t, square root of e to the x is just e to the x over 2. So this is my function right here. This is e to the x over 2. And then we still have to mark it with an arrow. Our initial point, if you go back and look at this problem, our initial point, it starts at 9 and goes to infinity. Well, if I plug 9 into here, right, I just get y equals e to the x over 2. So if I plug in 9, I get e to the 9/2. And if you do that on a calculator, you get this point here. So it moves up and to the right. Plus, that makes sense, right? As we can see from this, as t gets bigger, e to the x gets bigger. And here, as t gets bigger, y gets bigger. So it goes up and to the right, like that. So the arrow has to mark up and to the right. Okay, we got one more topic in this video. Not a real long video. And again, I'm making a separate video for a couple of the homework problems. So if we have two parametric equations, there's intersection points that we know about. That's where the paths intersect. But a collision point is an intersection point where the particles are also at the same place at the same time. And if the particles pass through the same point but at different times, those are just called intersection points. So the way we do this is you find the intersection points, and then you work out the values of t for both equations. If the values of t match, and both of them give you this point, then it's a collision point. And if it gives you anything else, it's not a collision point. All right, so the first thing we're going to do is find the intersection points. In this problem has a lot of algebra, so make sure you're keeping track of what the two curves look like. The first one is just 2 sine t, 2 cosine t. And the second one is this one. But one thing to notice, both equations only deal with sine and cosine. And the period of sine and cosine is 2 pi, and both of these t values only go from 0 to 2 pi. There are other problems that could come up where something might go around and around and have like multiple intersections. This doesn't happen. If we find the intersections just with algebra, then we found all of them. And then we're going to see if they're collision points. So again, I graph them first, of course. And I can see that there's 2 intersection points. We think we know what this point is, but we're going to use algebra to show what it is. And this point, so this one looks like negative 2, 0. And this one looks like a little bit less than negative 1. So this is like negative 1.2 or something. And then up here, it's hard to tell what the y-coordinate is. Like 1.6 or something. So the way we do this, to find the intersection points, we eliminate the parameter in both parametric equations, then substitute one of the equations into the other. So this sounds really hard. It's not, but it does have a lot of algebra. So here's my first circle, right? We can see that this is the large circle here because it's sine and cosine, centered at the origin. And we can see that the radius is 2. So using the same general form of a circle, it's not shifted, radius is 2. You just get x squared plus y squared equals 4. The other circle, the smaller one, we can see it's radius 1, and we can also see it's shifted left 2 units and up 1 unit. So just plug those numbers into the general equation of the circle. Remember, it's x minus the center. The center is negative 2, so the x-coordinate is negative 2. X minus negative 2 is x plus 2. And it's up 1 unit, so it's y minus 1. And then what I'm going to do is I'm just going to FOIL this whole thing all the way out. Simplify as much as I can. And then I'm going to substitute the other circle equation into this equation. So what I've done is I got x squared plus y squared here. I'm just going to plug in 4 into here. Right? So 4 plus 4x minus 2y equals negative 4. I just keep simplifying until I get an equation for y. So what I found is that the intersection points of those two circles lies on this line. Then I take this line and I plug it back into this equation. You could plug it into either equation, but it's much easier to plug it into this one. Just plug it straight in. Do some algebra. I'll let you fill in the intermediate steps. You're going to have to do it on tests, so make sure you know how to do it. And you get this equation, this factors, luckily. So the intersection points are at negative 6/5 and x equals negative 2. I don't need to check the y-coordinates yet. In order to check if something's an intersection point, I only need to check the x-coordinates first. If the x-coordinates match, then I need to check the y-coordinates. If the x-coordinates don't match, then it's not a collision point anyway. Right? This is basically what I just said. So what I'm going to do, I'm going to go back to the original equations of the parametric form of the equations of the circle. I'm going to find the values of t where collision points would need to happen if they are in fact collision points. And what I do is I'm just going to set the x and y coordinates equal. So here's the x coordinates. So this is the first circle, this is the second one. So I'm setting the x coordinates equal. Here's the y coordinates for the first circle and the second circle. And I need to solve this system of equations. So I take this equation here and solve it for sine t, right? I just subtract 1 from both sides. And then I'm going to take this part and plug it into the first equation. Right, so this sine t, I'm just plugging in 2 cosine t minus 1. I solve that for cosine t, and I get 3 cosine t equals 0, which is the same as cosine t equals 0. So t has to be either pi over 2 or 3 pi over 2 or both. So you just plug these in. If the x-coordinates don't match, then it doesn't matter. If they do match, then I have to check the y-coordinates. So I plug t equals pi over 2 into the x-coordinate for the big circle, and I get 2. Well, 2 is not negative 6/5, and it's not negative 2, so not a collision point. Remember, if the x-coordinates match one of my collision points, then I have to check the y-coordinates too. But this first one, the two graphs aren't even close together at pi over 2. Now I check 3 pi over 2. Again, I just plug it into the first equation. And I get negative 2. So this could be a collision point. But I need to check the y-coordinate, so I do that. And it turns out I get negative 2, 0. And you can see from the graph that negative 2, 0 is an intersection point. And so because the x and y coordinates match, then it turns out it's also a collision point. If you want to, go ahead and check these numbers in the other equation, and you'll see that both equations have the coordinate negative 2, 0 at 3 pi over 2. But we already substituted one equation into the other, so they have to match. All right, well, that's it for this video. I'm going to do another video right now that's going to show you how to do some of the homework problems. So you'll be able to do every homework problem except the last 6. The next video is for just the last 6 homework problems. So if you want to just stop here and go do like the first few homework problems, you've seen everything you need to see for the homework. But if you want to watch the other video now, feel free to do that. All right. See y'all later, and let me know if you have any questions. All right, bye-bye.